Alright, so for number 10, we are doing the enthalpy of fusion and vaporization, that type of problem. So we're looking at basically the melting and boiling points. If you guys remember this right here, as we put in energy into the system, the temperature is going to go up, but when it's melting and when it's boiling, it's going to flatline until all of the particles are separated from one another. Okay, so the flat lines represent the melting point and the boiling point, and then the angled lines are going to represent when it is a solid, when it's a liquid, and when it's a gas. Okay, so we're going to take a look at the information that we're given and just see if we can figure out how many lines we need to cross for this problem. So it's telling you to determine the amount of heat needed to take 20 grams of solid aluminum, right? So we're going to start on the solid line somewhere, at melting point to liquid aluminum at 1200 K. So we're going to take it from solid to liquid. So our ending point is somewhere on the liquid section. I'm just going to put it arbitrarily in the middle, and that's going to be at 1200 Kelvin. And then it tells you aluminum's melting point is 933 Kelvin. So that means this line right here is going to be 933 Kelvin. And then it gives you some information. It tells you that the molar capacity of liquid aluminum is 1.088 joules per mole Kelvin, and the heat of fusion is right over here. Okay, so it does not say, or sorry, one last thing I forgot to mention, it's at boiling point, at melting point, so we're starting at the melting point for the solid. Sorry about that, guys. So this is our start right here. So what we're doing is we're going to first fully figure out how much energy it takes to fully melt the aluminum, and then the second step is to figure out how can we take it from the melting point to 1200 Kelvin. Okay, so that's the two steps. Alright, so let's do our first calculation. So our first calculation is basically going to be about melting the aluminum. Okay, so this is our melting calculation. Alright, so when we're melting, we're going to be working with the heat of fusion. So it's going to be Q, the heat is equal to the mass times the delta H fusion. Okay, but for this one, you got to be very careful with the units of measurement. If you notice, what is the original unit of measurement given for the amount of aluminum we're working with? Grams. We're given grams. But if you look at the heat of fusion, it gives you kilojoules per what? Mole. So we got a discrepancy here. And so the first thing we actually need to do is we need to convert our 20 grams of aluminum into moles so that we can use this conversion factor right here. I think I mentioned it while we were learning it. But just be very careful about the units of measurement. Sometimes they'll give it in grams, sometimes they'll give it in moles, and so you just need to be very careful with the conversion. So, real easy. 20 grams of aluminum, if you look on the periodic table, is 13, right? No, 26. 26 grams per mole. Okay, so we just do 20 divided by 26. And that's going to mean that 20 grams of aluminum is equal to 0.77 moles of aluminum. Sorry, guys. It's 27. I try to do it off my head. It's 27. It's not going to change our number very much, though. 0.74. My bad. Alright, but any questions on what we went over so far? Just a general premise, the two steps. We gotta convert to moles first. You guys good? Okay. Alright, now we can just plug in what we got. So for the melting portion, we're gonna take our 0.74 moles of aluminum. We're gonna multiply it by the heat of fusion, which is 10.7 kilojoules per mole. And as you can see, the units of measurement will cancel each other out. And then it's just multiplication, and that'll give us the amount of energy needed to melt our 20 grams of aluminum. And that should give you 7.93 kilojoules. So that is how much energy it takes to just melt the aluminum. Okay, any questions on that first part? It's chilling. Okay. All right, the second line that we are looking at is we're basically taking our new liquid aluminum, which is at 933 Kelvin, and we want to take it to 1200 Kelvin. Okay, so we're just heating up the liquid aluminum now. Okay, so this one is just the calorimetry thing that we learned, Q equals MCAT. The only difference is that for mass now, we're just going to be using moles because the molar heat capacity is in moles. So we'll take our 0.74 moles of aluminum, so 0.74 moles. We have our C value for liquid aluminum right here, which is 1.088 joules per mole Kelvin. And then our delta T is the change in temperature, so it's going to be 1200 Kelvin minus 933 Kelvin. And that's it. Just plug and chug in your calculator. So I'm going to give you guys a minute if you guys need to copy any of this down and see if you guys can get the final answer. There is one little thing you have to do before you finish up the answer, so I'll give you a little hint on that. But take about a minute or so, see if you can find the final answer for this problem. Okay guys, let's go to the final answer. So if you multiply this out, you should get 214.97, about 215. Everybody good with that calculation? Yes? About 215? Okay, what's the unit of measurement for this this number? Joules. Yeah, if you what is it? Oh my gosh. If you cancel out the units of measurement, right? The moles cancel out, the kelvins cancel out, you're left with joules. Now, this is important because if you notice, what's the problem with just adding these two numbers together?
Because the other number is
kilojoules. Yeah, kilojoules and joules. So keep that in mind. So you either need to turn both of them into joules or both of them into kilojoules. So I'm going to convert to kilojoules, but I'll give you the answer in joules as well. So for kilojoules, you just move the decimal 3 times to the left, and then you'll get 7.93 plus 0.215. And so your final answer will be 8.145 kilojoules. Or if you convert it to joules, just move the decimal 3 times to the left, you'll get 81.45 joules. It does not specify to give in joules or kilojoules, so you can give it either way, and your answer is totally fine. If they ask for specific kilojoules or joules, just make sure you give it in that correct answer, or the unit of measurement they asked for. Alright, so let's start with 11. 11 is pretty simple. If you take a look at chlorine on the periodic table, how many shells does chlorine have? Okay, so if we look at chlorine, right here, it has 3 shells. Selenium has 4. So that's pretty much the reason why. Okay, so if you take a look, if you want to explain your answer, you could say something along the lines of chlorine's valence electrons are closer to the nucleus than selenium's. Something along those lines. You can mention the shells if you want. You could talk about how chlorine has 3 shells, selenium has 4, so that's a greater distance. So you could talk about the atomic size that way, but this is like the most concise way. The key thing I will mention though is because you are comparing 2 elements in your answer, you want to talk about both of them. You don't want to just talk about chlorine. You want to compare the 2 in your answer. Okay, that is actually an area a lot of people lose points because they'll just talk about one part of the question. You are specifically asked to compare chlorine and selenium, so you need to talk about both in your answer. Okay, yours can be a bit longer than mine, but I'd say this is as concise as you could probably make it. Okay, let's go to the ordering them from smallest to largest. I have the shells, protons, and electrons for you up there because that's what we'll be looking at. I promise on the test you don't have this many. So if you can do this many, then the actual test one should be pretty easy. The key thing I do want to mention, though, before we start ordering them is talking about the ions. If it ever talks about an ion, it's referring to the most common ion. And a key thing to remember is that anions, they have the same number of shells as their neutral counterpart. But then the cations, right, sodium and magnesium, the cations, they are going to lose a shell. Okay, because cations, they are losing an electron from the valence shell, so that valence shell disappears. That's why if you look at sodium and Na+, the ion will have less shells. Same thing with magnesium. But if you look at like oxygen, the anion, they have the same number of shells. Okay. All right, so let's. It tells us to do smallest to largest. So let's start with the largest because we have a lot of 2's, but we just have 2 3's. So if you look at sodium and magnesium, they both have 3 shells, right? And so we need to go to the next level. The next level are the protons. Now, which one of these two is going to be larger? Sodium will actually be bigger. And the reason why is because if you remember, if there are more protons, what do they do to the electrons?
They shrink.
Yeah, they shrink. They pull them into the nucleus, and therefore sodium will actually be the largest. I know there are more protons, so a lot of people think, oh, that must mean that magnesium is bigger. But remember, protons are in the nucleus, very small part of the atom. And so sodium is going to be larger than magnesium. Also, you can remember the pattern on the periodic table. As you go left and down, they are going to get larger. Okay, and so if you look at the periodic table, magnesium is more to the right, and sodium is more to the left. Left side elements tend to be bigger in the same row. Okay. So that's another way you guys can think about it. All right, so let's take a look at the 2's now. Okay, there's a lot of 2's, and so we gotta compare the ones that we gotta compare their protons. So oxygen both has 8, fluorine has 8, neon has 10. We got 11 and 12. Okay, so we just talked about how if there are more protons, what does it do to the atom? It shrinks. So the ones with more protons are going to be smaller. So which one of these atoms is going to be the smallest?
Mg2.
Yeah, the smallest one is magnesium's ion because it has the most protons. Most protons, same shells, it pulls the electrons in, and therefore Mg2+ is going to be your smallest. Okay, what is our next smallest?
Na.
Yeah, sodium ion, Na+. Okay, next one?
Ne.
Ne, neon, good. Alright, now we are at the ones where you have the same number of protons and shells. So now we have to look at the electrons. Now, electrons have the opposite effect, right? If you have more electrons, what does it do to the atom? Yeah, they grow, right? And so let's take a look at, let's start with the smaller one. So fluorine and fluorine ion are going to be those 2 smaller ones. Okay, which one is smaller between the 2? Fluorine or fluorine ion?
Fluorine.
Fluorine will be smaller because it has fewer electrons than fluorine ion. So it's going to be F and then F minus. Okay, and then last but not least, we're going to get oxygen and O2 minus, and there you go, guys. We have our exhaustive list ordered in size. Okay, and again, the one on your exam will not be this long. You'll have a lot less. Okay, so for this question, we need to look at the table right here, and it gives you the element and then their first ionization energy and their size. Now the question is asking which of these options is the best explanation for the deviation in the first ionization energy of oxygen. So it's telling you, look at oxygen and notice the deviation. So if you guys look generally at the first ionization energy, if we're just talking generally, what do you notice as you go across the periodic table? Yeah, ionization energy generally is increasing, right? Which makes sense, right? Because as the the shell fills up, the subshells fill up, it gets harder to take out electrons from it. But there is one deviation, and if you notice, that deviation is at oxygen, right? Because it looks like oxygen's first electron is easier to take off than the one before it, nitrogen, right? So it's harder to remove the first electron from nitrogen than it is from oxygen. That's the observation they're telling you to make. So again, the observation is that oxygen, even though it's more right on the periodic table, it's easier to remove that first electron than with nitrogen. And basically the question is asking, why is that the case? So let's go through our options and let's see what they say. So if you look at A, it says the atomic radius of oxygen is greater than the atomic radius of fluorine. Okay, well, if you take a look at it, that is true, but that doesn't really have anything to do with our trend, right? The trend is comparing nitrogen and oxygen, not oxygen and fluorine. Because if we're looking at just oxygen and fluorine, the trend is continuing the way it should go, right? And so this is not going to be a good answer because we're not even looking at the correct part of the chart. Okay, let's look at B. Atomic radius of oxygen is less than the atomic radius of nitrogen. Okay, so we're looking at these two, and this is true. But if we're taking a look at the radius, right? If the radius is smaller, right? What does it mean about the ionization energy? It's going to be greater, right? But then that's not the case here because oxygen is smaller, but it's easier to take off an electron. So this option makes no sense. So I guess the reason why A is not correct is because it is unrelated to the trend. This one right here is just incorrect. All right, that leads us to C and D, and now we are looking at not just the shells, we're looking at the subshells, 2p, the 2p orbital. So for this, we actually need to look at the electron configuration chart. Let me see if I have room to draw that. Okay, so let me draw it. So if we're taking a look at oxygen, okay, oxygen's electron configuration chart, we start with 1s, we go to 2s, and then we go to 2p. Okay, so we're going to be looking at these. Oxygen has 8 electrons, so 1, 2, 3, 4, 5, 6, 7, and 8. Now, if you take a look at oxygen, the first electron that's going to be removed is this one right here, right? Now, if you notice, what's special about this electron?
It's paired up.
It's paired up, exactly. So this electron is paired up. And if you remember electrons, what do they do to each other?
They repel.
They repel each other. Now, let's compare that with nitrogen's electron configuration chart. Nitrogen has 7 valence electrons, and it also goes up to 2p. Now, if you look at nitrogen, 1, 2, 3, 4, 5, 6, 7. If you look at the first electron that will be removed from nitrogen, what do you notice about that? It's not paired. And also, if you look at nitrogen, the subshell has 1 electron each, so it has a certain level of stability, right? So we're going to kind of stable. And this is the reason why it's easier to take off oxygen's first electron. It's because it's paired up. If they're paired up, they repel one another. Okay, so oxygen, even though it is smaller, even though it's more to the right on the periodic table, because that first valence electron is paired up, it is easier to take out than nitrogen because it has a certain level of stability with 1 electron in every subshell. Okay, so that was a tricky one. I think I mentioned it like real briefly while we were talking about it. So if you caught it, great job. That means you're paying attention. And then this is just not true. Electrons don't attract. All right. Any questions on that? Pretty tricky question. All right, so like I said, a lot of people get this wrong because they see 3 different binding energies and they assume 3 shells, and they just automatically pick the atom with 3 shells. However, if we look at the PES data, each of the peaks tells us that it's about the subshells. So we are looking at the atom with 3 different subshells. So the first peak is going to be 1s. The second peak will be 2s. We're looking for an element, an atom with that is in 2p. So we're gonna look at, yeah, it's gonna be B. Let's take a look at A. Let's just go through our options. I'm gonna pull up the periodic table just so that we can have it in handy. So the first atom is 4 protons, 5 neutrons. Neutrons don't even matter. We're looking at beryllium. Beryllium's final level, or its electron configuration, is 1s2, 2s2. And so it's only going to have 2 peaks. If you look at B, B is 10 neon. And if you look at neon, its electron configuration is 1s2, 2s2, 2p6. And so that's going to be 3 peaks on the PES. Just keep that in mind. PES is about how many subshells there are, not how many shells there are. Okay, this one right here will have 4 peaks on its PES, and this one right here will have 5 peaks. Okay, so that's the little trick for this one. It's recognizing that the PES data, the peaks tell you about the subshells, not the shells. Okay. All right, let's move on. All right, I'll give you guys about 3 minutes to try number 15. For this one, again, try to make your answer concise. Okay, less is more. I'm not good at English. I don't like reading your work. And so just make sure that you try to make it as concise as possible. But try 15. Okay, so it's asking you what's the variation in ionization energies of carbon, and then it gives you this graph. So ionization, if you guys remember, is taking off an electron. So this is how much energy it takes to remove the first electron, second, third, fourth, and then you see that massive jump from taking the fourth to taking the fifth one. So this one's pretty simple. If we draw the shell model of carbon, okay, so we have 1, 2, 3, 4, 5, and 6. All right, so taking off the first electron would be right here. So it would be doing this. Second is doing this. Third is this. And fourth, if you notice, is special because fourth is where it loses the valence shell, right? And so once you lose your valence shell, carbon has a complete valence shell, right? And that's the reason why there's such a massive jump from 4 to 5, and it's because you have a stable valence shell once you remove the fourth one. So something along the lines. You can say something along the lines of IE5 is much greater than IE4 because after losing 4 electrons, carbon has a stable, complete valence shell. Okay, other things you can mention in addition to that, you could talk about how now the valence shell is much closer to the nucleus, right? And so it experiences a greater attraction. So you can talk about attraction to the nucleus being greater because less shells. Okay, you could talk about the atomic radius being smaller, so on and so forth. Okay, so anything along the lines is fine. You just need to make sure you talk about how 5 is much greater than 4 and then give a reason why. Okay, so the question is asking, what is the relationship between the ionization energy of an anion with a -1 charge such as F-? So we'll stop right there. So it's basically asking us to compare 2 things. The first thing is the ionization energy of something like F-, okay? And then it's asking to compare that with the electron affinity of a neutral atom like F, okay? So I'll write electron affinity, okay? Now, what I notice a lot is that people don't compare these two. They start to compare ionization energy of F- and the ionization energy of F. Okay, that's what a lot of people start discussing, which I heard, which is okay. You're not the only one. I think most people, for some reason, interpret it this way. Maybe they just get like really attached to the idea of ionization energy. But you are not looking at the ionization energy of F. You are looking at the electron affinity of F. Affinity means how much it wants it. So we're looking at how much F wants an electron. So if we, I think the easiest way to look at this is to write down a chemical equation to kind of visualize what's happening. Okay, when you have ionization energy, what is happening to the electron?
It loses.
It's losing an electron. So if we wrote this as a chemical equation, we would say that F minus, if we have ionization energy, okay, that means that F minus is going to separate into F and an electron, right? Because it's losing an electron. Does that make sense? Okay. Electron affinity, on the other hand, is how much F wants an electron, right? So that means that F is going to combine with an electron in electron affinity, and it's going to form F minus. You guys see the difference, right? Okay, now, if we take a look at these two equations, what do you notice about them? Yeah, they're the inverse of one another, right? But same but opposite way. Now, if you think back to our thermochemistry stuff, what happens with energy when you flip the equation? Yeah, negative. So same. So the technical term is same in magnitude, right? Same number, but it is opposite in sign, right? Because you got to change the sign from positive to negative and vice versa. So that's going to be your answer. What's the relationship? It's the same amount of energy. It's just opposite directions. Okay, easy way to think about that is ionization energy. You put energy into the atom to kick out the electron, right? So here, energy is going in. So this is going to be a positive number for energy. But here, we know that F wants to gain an electron, right? So when it gains an electron, it becomes more stable. So energy is being lost in the system. We're going to a lower energy state. And so we can even determine which one of these is positive and negative based on what we know. But the answer that they're looking for is same in magnitude, opposite in sign. And the point of this question I want to talk about is not on our exams anymore, but it's to really, really drill in the fact, read the question carefully. Okay, don't get really attached to one part of the question, because I notice a lot of people look at ionization energy and they apply it to both of them. But here it's asking specifically for electron affinity. So you're comparing those two things. Don't compare the wrong things. Okay, and that's my English lesson for you guys. Although I wouldn't listen to me about English. All right. Any questions about that? Make sense? All right, so 17's a tricky problem because it gives you some information that's honestly not that important, but actually this is important, never mind. So it tells you basically the first ionization energy of an oxygen molecule, right? So you got O2, the molecule, and then it becomes O2 plus when it loses an electron, and it gives you the energy for this process right here. And then it tells you this is similar to the first ionization energy of xenon, okay? So if we take a look at xenon, xenon is a noble gas, but if you remember from way back in the review, I think it was, yeah, right here. Which element do we say xenon is most likely to? Yeah, fluorine, right? And anyone remember the reason why it would react with fluorine? Yeah, fluorine is the most electronegative element. It wants electrons more than any other element. And so that's why fluorine can force even a noble gas like xenon to react with itself. So if we take a look right here, we're going to be taking a look at O2. Now, if O2 has a similar ionization energy as xenon, and xenon can react with fluorine, what do you think? Do you think O2 can react with fluorine? Yes, it can, because it has a very similar ionization energy to xenon. So the answer would be yes. Would you expect O2 to react with fluorine? Yes, because xenon can react with fluorine, and O2 has a similar first ionization energy, so IE1 to xenon. Okay, if xenon can react with fluorine, if an oxygen has a similar ionization energy, then fluorine can also rip off a oh my god, I just brain farted. It can rip off an electron from oxygen gas as well. Okay. What?
It's not O2, it's like a heart.
It's an O.
A 30-year-old man's drawing hearts at you. What do? Call the police. All right, everybody good with A? Okay. B is the one that's a little bit trickier. It's asking you to suggest a product or products of this reaction. Now, for this one right here, you guys kind of need to remember different reactions that we've looked at so far. So honestly, I don't expect you guys to know this. This is you'll get a better understanding of predicting things like this in the future when we learn a bit more chemistry. But the best way I can explain this is to think of a combustion reaction, right? Because if O2 is reacting with something, it's a combustion reaction. So what we're going to do is we're going to take a look. Oh my god, what happened to my mouse just now? We're going to be taking a look at one of the reactions that we are familiar with. Sorry. All right, so one of the combustion reactions that we are familiar with is H2 plus O2, right? It's the combustion of hydrogen gas, and this is how we produce water, H2O. And then we balance this out, right? So we put a 2 right here and a 2 right here. Okay, this is going to be a very similar reaction. We are reacting O2 with F2, and if you look at the structures of this reaction on the reactant side, it's pretty simple, right? You have a diatomic gas reacting with O2, and so we can make a similar assumption right here that it would form F2O. Okay, so instead of the hydrogens, you have fluorines instead, and then the balancing is going to be the same here as well. Okay, this one's a little less intuitive to get. You kind of need to pull from other knowledge from other things that we've seen in AP Chem so far. But this question will make a lot more sense once we go into the next unit, I believe. When we start drawing the molecules, it'll make a lot more sense. Okay, but our answer, one of the products that we can produce is F2O. That's the best one that we can get. Okay, another product that you can make is F2O2. So you can do that as well, but this is probably the better one to write based on what we know so far. Okay. All right. So for 18, it's asking you what electronic transition in a hydrogen atom releases the greatest amount of energy. Now we didn't talk super in detail about the actual distances and energy level, but you can kind of see it in this electron configuration chart right here. Now, these are the energy levels. Now, what do you notice about the distances in the energy levels as you go higher in number? Yeah, they start shrinking, right? They start getting closer together. So, the reason I wanted to talk about that is because let's say that you have an atom and this is your nucleus, okay? And we're going to look at the energy levels. The first energy level is going to be pretty far from the nucleus, okay? So this is n equals 1. N equals 2 is also pretty far, but not as far as this distance right here, okay? So it's going to be far, but not as far. And then as you go higher in energy levels, they get even closer to each other. So n equals 3, I'm just drawing them a little arbitrarily, but the point is they get closer. N equals 3 might be right over there. N equals 4 might be right over here. 5 would be even closer, so on and so forth. So when we're looking at the actual distances in the energy levels, the first one is the furthest, and the distance between 1 and 2 is the biggest distance, and it gets smaller and smaller from there. You can see it in the electron configuration chart. And so we talked about how when you go from the electron goes from different energy levels, it's going to release energy, right? And so we're going to be looking at the one right here where it's going to release energy. Now, first and foremost, one thing to remember, in order to go up in energy levels, okay, so if you want to go up in energy levels, you need to absorb energy, okay, right? Because the electron, the lower it is, the less energy it has. So to go to a higher energy level, it needs to absorb energy. However, when you are going down the energy levels, you are releasing energy. Okay, so that is an important thing to keep in mind as well. Okay, so first is the distance. 1 and 2 is the biggest distance, and as you go up, it gets closer and closer. And then if you go up in energy levels, the electron has to absorb energy because it's going from low to high. And then when it's going from high to low, it releases energy. So when we look at this problem, it's asking for something. It's asking for an electron transition that releases energy. That means we are looking for going from a high number to a low number. Okay, so which option here would not work? Yeah, D would not work because we are absorbing energy here, right? We're going from 3 to 6. We need to absorb energy to do that. All right. Next, we have A, B, and C. So let's start with the one that is probably the worst answer. Which one of these releases the lowest? Yes, C, because it has the 2 highest values. Okay, and so this one would be the smallest out of the releasing. Okay. So far, so good? Okay. Next, we're going to look at A and B. Now, the problem with this one that makes it difficult is that this is a drop of 1 level, and this is the drop of 2 levels, right? And so which one is greater? Now, the key thing to keep in mind is that 1 and 2 is the biggest distance. After that, it gets pretty similar from there. And so the answer will be B. Okay, if you guessed A, that's a good guess, but it's going to be B because you're dropping 2 energy levels. If this was 2 to 1, this would be the correct answer because 2 to 1 is the biggest gap. Everything after that gets kind of similar, closer and closer together. So the amount of energy levels you drop is going to be important. Okay, but it is not 2 to 1, and so your answer is going to be B. You're dropping 2 energy levels, and it's not the 2-1 drop. Okay, so we are looking at Ag+. So let's look at the periodic table. We're going to write the electron configuration and then the noble gas configuration. Okay, so Ag+, obviously it's Ag, so we're going to look at this right here. So pretty long electron configuration. We're going to go through the first subshell. So 1s2, 2s2, 2p6, 3s2, 3p6, and that gets us to here. Now we got to go 4s. 4s2, this section right here is the D subshell, but we got to drop a number, so 3d10. And then from here we go normal again. 4p6, 5s2 would be right over here. And then finally we get to the subshell that Ag is in, but we got to drop a number, so it'll be 4d, and then we count to 9. Okay? So a lot of writing. All right, let's go to the noble gas configuration. The noble gas right before Ag is krypton. What's up? Thank you, yeah. We dropped an electron, so 4d. Well, actually, no, it's 5s1. Yeah. 5s1. Thank you. Totally forgot about plus. So it's 5s1 because it's Ag+. That means you lose 1 electron. Okay? And we always drop it from the S subshell before the D subshell. So that's the discrepancy here that I forgot as well. Thank you for pointing that out. It's going to be 5s1 because you drop an electron from the 5s subshell before you do from the D subshell. Adding. Well, if you gain an electron, this would already be full, so you would have to add right here. Yeah, and also metals are never gonna gain an electron, so yeah.
Erase it. Erase it again.
Yeah. 3 after D right here. Yeah, the D subshell is always one level lower. So even though it's on the 4th row, the D subshell will be 3D. Yeah, so on and so forth. Yeah. All right, noble gas configuration. Its krypton is the one right before it, so Kr. And then we just kind of add on from there. Kr takes you to 4p6, so it'll be Kr 5s1 4d9. Okay. So those are your noble gas and electron configurations. All right, and then last but not least, for our chart, okay, we just need to plug in what we got. So we can go up to pretty much this level right here, 5s1, and then 4d9. So like that, and then just fill in everything else underneath. And that's it, guys. That's going to be the electron configuration chart and the writing it out. Just make sure everybody is paired underneath. And again, since it's He plus, you take off an electron, so you took off one electron from the 5s subshell right there.